Okay, good morning, everyone, and welcome to CUIIC Academy Webinar Series 51. My name is Anastasia, and I coordinate CUIIC Academy Webinar Series. It's great to have everyone joining us today, and we're looking forward to have a great presentations today. And before we begin, we would like to recognize and thank our 2026 webinar series sponsor, Ackerman. Their support help us continue providing educational opportunities and bringing the underground infrastructure community together. Thank you, Ackerman, for your continued support of CUIIC Academy. And for anyone joining us for the first time, CUIIC is the Canadian Underground Infrastructure Innovation Centre based at the University of Alberta. Our goal is to bring the underground infrastructure community together through learning, collaboration, innovation, and professional growth. Through expert-led webinars like this one, we create opportunities to share knowledge, learn from industry experience, and continue growing together. At the heart of CUIIC is our community. We bring together people from industry, academia, municipalities, and the next generation of professionals to exchange knowledge, build connections, and work together on real challenges facing underground infrastructure. That collaboration is really what CUIIC is about. Bringing different perspectives together and turning ideas into practical solutions. As part of CUIIC Academy, you can expect more than just presentations. Our webinars are designed to provide live learning, practical industry insights, and opportunities to engage directly with experts. And they're also free and open to everyone, and recordings are available afterwards, so you can always come back and continue learning. And before we move into today's webinar, we also want to invite you to join us at the CUIIC Fall Summit 2026, happening September 15th through 17th at UBC Robson Square in Vancouver. This year, we'll be focusing on two major areas: underground safety and pipeline rehabilitation, with 3 days of learning, discussion, and connection with professionals from across the industry. Registrations are open, and you can scan the QR code on the slide or visit our website, cuiic.ca, to learn more. And if you'd like to stay connected with us after today, you can find us on LinkedIn, Instagram, YouTube. We share our upcoming webinars and events, research, industry updates, and other CUIIC activities there. So you can scan the QR codes on the screen or visit our website to learn more about our activities. And with that, we're ready to move into today's webinar. At this point, I would like to introduce George Bontas, who will be moderating today's session. George, thank you for joining us today, and I'll turn it over to you.
Thank you, Anastasia. Thanks everyone else for joining. I think we've got a really interesting presentation coming up. Styrene is something that's it's a very hot topic in CIPP installations. Most often we see it from the perspective of air and steam inversions, where we have styrene released in those methods. Chris will talk a little bit about that, but this is a topic that's come up, and it's gaining more interest and observation, and that's how do we handle the styrene when we're discharging close to water treatment plants. And Chris will talk about several projects. We were involved with him and AECOM on a couple of them. The most recent one that he'll talk about in Winnipeg is a real eye-opener for the industry, I think. Next slide, please. Are you able to advance the slide?
I did that already. Sorry, it's
not showing up. Okay. Well, Chris Macey is our presenter. Right now, he's in Japan,
Mm.
and it's about 2 in the morning, so it's about bedtime there. Um, Chris has been involved in, as the slide says, he's been around for 45 years, and he's been involved in pretty much all aspects of assessment and rehab of sewer and water infrastructure. Um, he's over 35 years with CIPP, and there's no question that he's a leading authority in North America and abroad on a lot of the topics that we'll be talking about. He's been involved a lot in AWWA, ASCE, NACE, NASDT, and NASCO. In NASCO, he's a member of the TAC, the Technical Advisory Committee Council. He's also been involved in ISO. He was involved heavily in the design or the preparation of manual of practice 145 from ASCE, close design of close fit liners for gravity sewers. Um, bigger bigger things, I guess, or things that you may have heard of. He's been inducted into this NASTT No Dig Hall of Fame. He was also the Person of the Year, selected by Trenchless Technology magazine in 2025. And just this past month, he was awarded the Bechtel Award from ASCE at the UESI conference. So, with that, Chris, I'll let you continue with the presentation.
Okay.
One thing that we do have though is if you have any questions, yeah, sorry, if there are any questions, there's a question and answer tab at the bottom of your screen probably. We won't be able to answer questions in chat, but if you put questions into the Q&A tab, we've got some time set aside at the end of the presentation to address those. And questions that we aren't able to get to, we will ensure that the answers will be provided. Sorry, Chris.
No problem. I'm good to go. My screen's up. Good.
Perfect.
Awesome. So we're going to talk a little bit about some past work in close proximity to plants, a little bit about styrene and other VOCs, just kind of what are they? Is they something I know when I started in this industry was something we never even talked about in the context of, understanding the process of how we make CIPP. Uh, touch a little bit upon NASCO and sort of other industry emission and cure water studies. Um, the the work that we're going to talk about today is particularly um, relevant to what NASCO called their Phase 4 studies, and that started to give us, I think, the first hard understanding of the type of impacts that you could have on a treatment plant. We're currently working on Phase 5 studies, which is I'll touch upon kind of what Phase 5 is, and but really just some recent practical ramifications of CIPP in the plants. And I think one of the questions for a lot of people, and hopefully in Phase 5 we'll do a better job of answering, but what's close? Because in essence, to quantify, it's something that we haven't modeled a great deal. And in a traditional job site, we're not set up. So I have as George mentioned, a recent real close case study because we're working right at the plant. We're working there for a reason. We'll talk about it more at No Dig North. But how do we do this? What kind of tools we have, and once you do this in real life, it's kind of the tools you'd like to have. Uh, I know in literature, and I actually worked on a job before. I'll talk about in a second with in situ form and in situ form job. I did not work on this job, but it was one of the first documented, daring efforts of lining the interceptor right into the plant. And at that time, it's well documented in the NASCO paper that's cited below there. Really, really. challenging install, just the bypass of it, and not really reported a great deal, but that job was monitored uh, um, very, very comprehensively to try and understand styrene residual. Like they're very cognizant of it. They're cognizant of it, and the level of treatment in the plant. The focus was more on kind of the flow through and the impact of of it when it left the plant. But it was kind of the first time I saw it documented in a paper. My first exposure was in another in situ form job in Vancouver at the Iona plant. That picture you see at the bottom is right across the Fraser River from the plant, and they did three in over kind of 2010 through 2012, three shots. My role in those jobs was primarily related to a traditional role, but it was the first time that I started to see real numbers. They're small there because they're intentionally small, but it was the first time I'd seen, hard data that looked at the VOCs and looked at the impact of the treatment process. These were huge shots across the Fraser 1700 millimeter diameter tube. You can get a sense of how long those shots are in terms of, over the whole wet outs. And the outlet was literally right at the interface to the plant. And the cures went on for about 5 to 7 days of the ones that I saw, and it was really eye-opening in terms of looking at the chemistry and a great deal of deep dive. Iona at that time was a primary plant, so again, the focus of the monitoring was not on the impact of process, but the focus of monitoring was the flow through and what happened when it flowed through a primary process and in terms of its impact or potential impact on fish habitat. The NASCO studies really started with the um, a lot of literature that came out in kind of the mid 2017, 2016, and it was a lot of questions about the literature that were there in terms of it. So the first phase of NASCO studies were really on just to look at the science of it, to see what was out there, and there was a very strong conclusion that there was a lot to learn. And the phase two studies, which was heavily involved with the group, was looking at worker exposure and indirectly at public exposure in terms of, safety. And specifically, and I think it's one of the things that really, really brought it to light was as we went into air inversion steam cures, you have a plume and you have it very, very, out in the worker's face. So to understand that, and the 2020 studies were very, very quantified. I've used the Army Corps of Engineers from the monitoring side. So finally had someone who knew the importance of doing background. We talk about a VOC like styrene. It's in everything that's out there if you go look for it. So if you don't do background work, you can't do clear work. So we brought in very, very competent people to go and do the monitoring, and Louisiana Tech did the hard modeling and the study, and then the phase three studies were focused on stuff that I think we'd learned in there is just basically the ability for styrene to migrate. It as a VOC, and like a lot of VOCs, it knows nothing of Newtonian physics. So basically, its ability to permeate and move by diffusion it makes it a tricky thing to work with, and it'll literally go through that non-structural layer in there. And we learned a lot and moved that into the phase three. The phase four studies were specifically related to the impact on processes, which I'll talk about today, and you would be remiss if you kind of didn't go back to really the first time, I recall anyone looking at styrene from a management perspective was the city of Toronto. And that 2001 report is just an excellent report. Hot water cures, but trying to understand, didn't one of the things that I don't think we appreciate as engineers is that, and we didn't, at least I didn't, write the building code, but we have this interconnection, with through the plumbing system of that. And that was a real eye opener in terms of looking at at levels and the value of the interface with plumbing. And similarly, that 2020 study that Dennis Piven, when he was with Aegon Situ Forum and Mark Knight did with University of Waterloo, were really, really informative in terms of quantifying the effectiveness of a P-trap and the mobilization of styrene in air. But the phase 4 studies were done through BAMI, through Dr. Isley's group, University of Purdue, and there was an awful lot of lessons and an awful lot of knowledge I know learned. So. Styrene has, you look at a polyester resin that we look at in sewers, and if you do an IR spectrograph of it, you'll find from the very, very first install in 1971 to the resins we know now, we've basically modified that resin to make it more workable. We've done things, but the VOC in it historically is there, and it's the same VOC. It's the most common VOC. It's the one that we know the most about. Styrene gets um, if you drink it in the wrong form, you'll get very sick. It is a very, very, it can be a very harmful thing. But in essence, if you look at it in terms of the levels at which it is very manageable from a practical perspective. And styrene, if you're going to do a water cure, is going to be present in a curing water. It'll be in a steam cure. It'll be there. We don't talk about it a lot in a UV cure, but in UV cures, actually, there's like a burp of styrene in the context of it, so they're not styrene free in the context of it, and styrene's out there. One of the raps about styrene is you get odor controls, and odor actually in the context of styrene, because the odor threshold is so low, is a real advantage for working with it, because you can smell it long before it is a problem for you. So. The driver for the phase 4 study were reports that basically could impact biological treatment, at wastewater treatment plants, and that was a real concern. And obviously, if you take a wastewater treatment plant out of service, it is a big deal, and that was the primary concern, the primary driver for it. In the study portion of it, it was to, one, do hard quantitative work to evaluate the effects of styrenated cure water on biological treatment systems. And I'll talk about that in a minute as to why biological treatment systems were focused on. And then the kind of the real focus was to try and provide wastewater treatment operators with a reliable, estimate of to quantify at what level styrene could impact treatment processes, and as I mentioned, there are biological treatment processes looking at biomass type processes in the phase 4 study, and that was kind of the focus of the study. Styrene is I've worked at different times in my life with VOCs and the whole family of VOCs, and I don't profess to be my discipline. I'm a pipe guy and line and understand structure, but VOCs are a really, really unique family of things that we deal with, that are out there. They're easily volatile from water. Will come out of water or solution, so that they will be there if you're a worker and you're walking around, and there's the length of exposure has as much of an impact as the duration. But when you're talking about worker air exposure, you're usually talking in the 20 ppm level. If you're looking at the styrene that comes out of all of the things in nature, not in nature, but in manufacturing, that use styrene, basically the EPA drinking water stuff starts to go down to zero point 0.1 milligram per liter. So now you're talking, less than parts per million. You're looking at the part per billion, threshold. Um, the thing that we'll talk about here in terms of when you get into freshwater biota, the no observed effect concentration, which I'll talk about, is it can be anywhere from about zero point 0.1 to 4 milligrams. So that work I talked about at Iona earlier, the concern was the flow through and what's the impact on the water course. So um, talk a little bit about that in the context, because at four parts per million, basically you can smell styrene. It smells like glue. At 0.01, to zero point 0.1, depending on people's olfactory skills, you start to get below the odor threshold. So basically, from a practical perspective, whether it's NASCO or anyone with common sense, if you're going to a receiving stream that has fish habitat or aquative, any type of life in it, that you intend to have life in it, uh, we would recommend treatment, and it is standard practice. And we've learned a lot, especially in the Canadian market, of supplemental type treatment work that we can do. And I will touch upon that because in recent projects we've been working on, we can actually get it down to levels that we never thought we had, from a practical perspective. So wastewater treatment plant operators are nervous about styrene affecting their processes. And that's not a criticism, that's a reality of it. There's not a lot published on it. And that was one of the reasons that the phase 4 studies were driven, to get us a better understanding of it. The work that was done under this looked at 8 large databases, in terms of publications, found 200 that got shortlisted to about 26 that passed the test of both peer review and that were provided really meaningful information. And basically, when you got down to water quality artifacts, there was about 6 publications of looking at literally thousands and thousands of publications down to that were really there. And from a practical perspective, in terms of that research, we couldn't find or they could not find a single peer-reviewed research that actually took what's called a publicly owned treatment plant offline in 5 decades. And that doesn't mean it's not possible, because the testing that I'll talk about is definitely possible. But we couldn't find one in the context of a peer-reviewed research one that provided a meaningful test case study to go and look at. And the reality is that there's other reasons that a treatment plant can be upset. And styrene, because of what it is, and if it's there and it gets at an elevated VOCs, and biological treatment processes are not friends, and that's not surprising. But if it's out there, it is something that you need to know, and that was kind of a big driver for trying to drive the study. In the phase 4 studies, they were looking at 3 different processes. They're all what we will classify, and I'll talk about in a moment, of biomass style of treatment processes, which means they're very, very sensitive in terms of that. I'll talk about in a second. The Charlotte Water, the HRSD, Hampton Roads, and Metro in Nashville. 3 different plants, but all with the same style or characterization of process. And uh, working on a job that I'm going to talk about in a minute here, uh, I am not a treatment person. So I have a fella that I work with named Keith Sears, and Keith Sears is one of our global leads at treatment. And before we worked on the job that we're working on, gave me a lesson in the difference between biomass and BOD driven type processes. If you work up in our part of the world where you have winter, it is certainly more common to have BOD driven processes, just because of they need to be resilient. They need to deal with the large temperature swings, the environment. But biomass driven processes are, if you look at them on paper, they can handle fluctuations in load, but compact footprints, less handling, basically less energy, more efficient. But the reality of that is that if you blow up a biomass-driven process, uh, the anything that just nitrification, denitrification is much more sensitive to biological curves being thrown at it. So it is much more sensitive to styrene than a BOD driven process. And the other thing that certainly was a lesson taught to me by Len Osborne from the early years of working is one of the biggest things that we need to be cognizant of that we sometimes forget is temperature variation. And I'll talk about that's a really, really important thing is temperature variation can play a significant role in both processes in terms of upsetting them and the recovery of the sewage treatment plant. The key findings out of the biomass studies were basically for those three sites that they looked at was that if you get to the no observed effect and you keep basically styrene levels to less than about 2.3 milligrams per liter, is that they did not have a measurable impact on process. The other thing they found is that these processes were quite resilient, is that they could get to kind of the concentration of about 100 milligrams per liter. And basically, if you didn't destroy 50% of the biota, or the biological in the process, you had a huge disruption on the process, but it recovered. And then if you kind of take those numbers and look at, what do we know about styrene? We don't do a lot of measurement of it, but a very good cure in a typical hot water cure or a steam cure, if you've got the residual that you're dealing with, is about 50 milligrams per liter. It's not uncommon for them to be in the 50 to 200. And quite frankly, since we don't measure it, and I've looked at some ugly, ugly cures, I would suggest that inadvertently you can see numbers that are much higher than 200 milligrams if we're not focusing on the cure. But 50 to 200 milligrams per liter are not unusual numbers that we've delved into that we can see, depending on the degree of uh, of diligence taken in terms of curing. And appreciate curing is a good thing, not a bad thing. It's how we build the long-term properties. If we can get styrene to the closer we can get styrene to a non-detect level, the more of it is converted into the structure and buys us life. So the other thing that you know that we see in typical plants is that styrene is not normal at very high levels. You will see them typically at very, very low levels, less than a milligram per liter, and in essence, as I mentioned, that you can actually treat them. The treatment process that we do in Frenchwater experimented in recent years with things from activated carbon to thermal oxidization, chemical scrubber, biological treatment. By far, the most common one that I have been exposed with and I've seen in industry is activated carbon. And I think the biggest stress level that people have is that activated carbon level is very, very effective. It's very simple to use in the context of it. So it's kind of meets the elegance bar. And I think if you're a treatment purist, probably the things that irritate you is that it could be used much more cost effectively than it typically is. So we don't use it very cost effectively, but it is, when we're in the context of what it prevents, sometimes is a very, very valuable thing, and it is a really useful thing to have in your toolbox. And I will touch upon that at the end of this. The case study that George is talking about is a job that came up. We'll talk about it at No Dig North this year, and it was a major upgrade. It was driven not by um, it was driven for other reasons in the context of the benefits to renewing an interceptor to facilitate very, very complex construction. And but the shot that I know kept George up at night and anyone else with a conscience was an over-the-hole wet out and about 400 meters of a 1500 millimeter concrete hose pipe, and it was 180,000 pounds of resin and in a 37.5 millimeter tube, and it was deep. It was about a 12-meter deep install, actually deeper in some spots. That plant was a BOD based plant that treats about 65% of all the wastewater for a city of 850,000. So it's a very, very critical thing. And taking a plant like that offline, you need a lot of lawyers just to defend you from a practical perspective. Um, the the reality is that we don't have studies on a BOD based plant. And a BOD-based plant, based of the theoretical work that we did, thought that it could take literally about 25 milligrams per liter or something higher, but we had nothing to base on. So the objective and the manner of doing these and the risk that you're managing is something that you genuinely have to give some thought to in terms of how safe do you be. Uh, we did this contract and set out with a hard contractual objective, a requirement to look at biomass limit states. So we're looking at a contractual requirement and a technical objective to keep it under 2 milligrams per liter. And the scary thing about this one is we weren't going right into the plant, but we certainly were close enough. You're about 100 meters away from the intake. And like most plants, you're not only dealing with things, you've got basically multiple inlets. This has a triple inlet. We were dealing with one of the three interceptors that came in the headworks of the plant. The contractor, and I don't have to hide who the contractor was in this case, but they knew through diligence, and if someone has done monitoring on it, they have done probably more monitoring than anyone. And I would encourage as part of the protocol that we do to take a closer look at residuals. There's a lot of benefits to understanding that if you're getting 50 milligrams per liter in the cure water, you've done a very, very good job. You've likely achieved a degree of cure of somewhere between 97.5% to a full cure in the liner. And that's consistent with, like I said, in the context of ones we've seen, whether it's 50 to 200 or 250, um, that means that someone's done a work, at doing rigorous cure. In the context of this specific job, the contractor had proposed using ammonium. I can barely price, so I call it APS. They use an additive in it to basically their objective with that additive in the cure water was to take that 50 milligrams per liter and turn it into 10 to 20. That was kind of a part of the process. The the reality of this is all a good plan, but how do you measure this? Like, what do you use? How do you structure a contract around it? And this was something that was done on an emergency basis. This was a lot of work and a lot of work done safely with risk management, but under pressure because there was a lot of money involved in the context of the work that was done that had nothing to do with styrene in the context of it. The primary measuring devices that we have in industry are PIDs, direct read devices, passive dosimetry. That doesn't help you to see the fluid. That's for styrene and air. And we're currently in the phase 5 studies realizing what a gap it is in industry to not be able to. I can stick a thermometer and measure the temperature of water, but I can't stick a device in the water, in the waste stream to measure styrene correctly. And there are devices out there, they just haven't been piloted or brought to market. And that is a big part of the phase 5 studies, was to try and provide ways to do this. And I'll talk about what a challenge that is from a practical perspective on this case study we're talking about. The other curve that this case study had, we were focusing so much on styrene, we really never thought about temperature. And it was quite a casual conversation about to the process engineer of letting him know that that our discharge was 100-degree Fahrenheit water, and that caused tremors in them. And then, especially in the wintertime, basically, when we looked at it, a typical winter waste stream in this application is kind of 8 to 10 degrees centigrade. I'm working with something that's 30 degrees centigrade in terms of the fluid coming out. And the maximum acceptable spike that they told us is if we raise the temperature at the influent 7 degrees C, we'd basically it was as bad as the styrene. So that was a big deal. So we were focused very, very much. And the epiphany of, the practical aspects is that styrene, because there's no device, is it, and I deal with this on jobs, a lot of jobs in the last year now, is that it takes about a day and the labs don't work on the weekend. And the labs don't work, they don't have the same constraints that they have. They're not as available. And in the context of this job, they paid the lab to work on the weekend, but it still is like a 24-hour period to understand what styrene is. And one of the things that became an epiphany is that if you looked at how styrene dissipates and heat dissipates, the majority of that process is dilution. There is in the context of styrene, there's what we call a half-life effect because it actually just goes away. It dissipates very, very quickly. We found that in steam cures. In heat dissipation, you have dilution and the heat loss effect. So these two things are there. Dilution is really easy to estimate. Quite frankly, the half-life effect is one of the things that we're trying to do in the phase 5 studies to get a better understanding of how close is close, in the context of the residual styrene there. But the dilution is 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 there. And similarly with heat loss, the heat loss effect is quite pronounced in the wintertime, not as pronounced in warmer climates, but it's kind of what the temperature dissipates. The epiphany to this is that they're the same formula on the dilution side. And that was a real eye opener because we thought about it, but just it literally is when you look at dilution, and if you can mitigate and solve your problem with dilution, it's very conservative because you have a half-life that's going to make it less. And in the context of the heat loss will always be less. So you'll be over predicting if you just manage your problem with dilution. In essence, it's a safety factor because there's actually more loss or more dissipation of them. So the dilution effects, like I said, they tell us a very similar stories. Uh, they're the identical equations. You're looking at, the volume you're dealing with and the concentration, mixing it with some raw stuff that's not contaminated in the context of a traditional job. And the temperature side, same type of thing. It's the exact same formula. The flow rates are really the same because we're taking, the site that we work at that has cure water, and we're typically have a bypass if we're working near a plant because we've got a huge, these are larger pipes. And if we know the flow rate of the bypass and the release rates of that we're pumping it out, you basically can calculate dilution. As I said, the styrene fluids go to a lab, the temperature you can measure in real time. And when you think about it, one of the things that you're doing on the job and you need to structure into your contract is that you're not only measuring temperature on a CIPP, you're routinely measuring it with precision. So all you have to do, and all we did on this job, was repurpose the exact same devices that we use to monitor CIPP cure to convert them into giving us insight as to what the residual styrene would be that would take 24 hours every, it was once a day you could figure out what that was in the context of monitoring. And the amazing thing about this is that on the results of this job, the results of the pre-work by in situ form is that they didn't get down to the 10 to 20, but they got to literally 22 milligrams per liter by APS. Now, APS is a very, very effective thing. One of the practical things about APS is that basically if you continue to use it, your boilers will die. So there's practical reasons to not do it. But in this case, because we were targeting such a low one, and the dilution calculation that we did basically had calculated that the dilution process that we had in managing the flows and managing the time is it predicted that we were going to get down to zero 0.1 milligram per liter versus a very conservative target of about 2.3, which is again for a BOD driven process is a got some safety factor into as well. The actual measure that we got when we did the blending was we got it right down to literally the part per billion level to 0.037 milligrams per liter. Similarly, if you manage to the degree that we were managing water, the temperature in this was literally a degree of a blip, not 7 degrees of a blip. And as a result, the wastewater treatment didn't even burp. They didn't even know we're there. Uh, a word of caution, and this is when you go and get VOCs back from a lab. This is a sheet that I got on this job, and you'll see that number of 36.6. I just about had a heart attack uh, because I thought it was 36.6 milligrams per liter, and they report VOCs in the micrograms, so at the part per one level down from part per million. So that was 36.6 parts per, micrograms, not milligrams per liter, and that's 0.037. So after not having a heart attack, I felt better and and got some more accurate flow data on it and found, got again the dilution will give you a number, a target number if you work to your dilution number, and you do a lot of digging on the rest of the process, the half-life process, the similarly on the heat loss side, you can do some work to get a better appreciation of it, but keep that in your pocket as a safety factor from a practical perspective. So in the context of it, it just we've come a long way since styrene was just something smelt and stunk. It was, smells like glue. And we definitely know how to, define its risk to workers, the public, and the last 10 to 20 years have taught us an awful lot about how to do that safely. Um, there is no question. It's not a flippant thing. If you take a sewage treatment plant off, you have a major impact on the environment. And the these two questions of kind of how close is close and how do you mitigate them are really important issues, because a lot of interceptors don't get rehabbed, like even the interceptors in the case study you showed here were probably, if they were anywhere else in the system, would have been rehabilitated sooner, but weren't there because of how complex it was, or how complex it was perceived to be. So those are, the most critical pipes you have without question in the pipe. So to be able to line those in a cost-effective manner at a fraction of the cost of replacing them, and buying a new life in that context, and making them more resilient structures, which are all lessons we learned in it. But a big part of that is understanding a plant across disciplines. Someone with my background and someone with a process background rarely talk. Like, we don't talk in the context of it. So you have a lot of tools in the toolbox, and this communication outside of your discipline is a really, really important aspect of, especially this aspect of work. So many tools in the toolbox. We just need to determine, what are the right ones for the applications, and that is kind of the core, lessons learned in this type of work, and in the case study I'm talking about, is that you need wastewater treatment on your lining team. You need that type of expertise. You need to actually talk the language of the plant. Every plant is different. They have different systems, different time cycles, different ways that are convenient, and the communication of it. Every plant is different. There's maybe BOD-driven plants and biomass-driven plants, but as I have humbly discovered in the last year, every plant is subtly different, and there's enough reasons for the plants to burp, and if they burp and you're working with a VOC around them, you're the logical person who caused it to burp. So you need to understand how to do that. The monitoring includes not only temperature and styrene, but from a practical perspective on this case study, I would love to tell you that I had, thought out a wonderful protocol to do it. The flow was there, the flow monitoring was there because the contractor was diligent and we're very, very focused on it. It needs to be structured contractually into what you do to, how you monitor it and how you do it. So knowing temperature and styrene without flow is an equation with more than one unknown. And I will tell you, knowing flow is really, really critical because dilution and flow tells you just an incredible amount of information of both styrene levels and temperature, and they correlate very, very well on dilution side. It's a very practical way. You need to fully vet risk in this type of work because it's not a simple answer. Like to understand what safety factor is, the ramifications of doing it wrong very high. Like in our case, even though we, looked at it from a practical perspective and saw a BOD based plant that maybe we could put 20, milligrams per liter in, there's no textbook that's been written to say so put it in at 24, from a practical perspective. So the NASCO work on biomass driven plants, but you need to sit about, how you manage that risk in the context of what is a safe level to do. And jobs since this case study where we look at more stringence of bringing in the treatment things, of bringing in things beyond just the styrene management to do, but to be able to predict it and do that is very, very important. The phase 5 work that I think you'll see come out next year will be just hopefully the next chunk of that road into understanding not only the toolbox, but updating it in the context of in-field measurements. So you're not waiting a day, but to put together a substantial best practice guideline to achieve successful installations in critical locations like that. And with that, I'm only 2 minutes over, and George will be excited that I'm only 2 minutes over the time I was talking. So with that, if there's any questions, we would be
Yeah,
happy to
Chris,
entertain them.
we
I'll
have
turn the audio back.
one question, Chris. It's
Mhm.
is UV curing the preferred approach to limiting discharge of styrene during lining processes? Is there an increase in costs associated with the use of UV curing as opposed to steam or water?
Yeah, so Paul, UV is certainly one of the tools you have in your toolbox. UV, as you get closer to the plant, uh, often hits a brick wall in terms of some of the larger pipes we do, and and to uh, I don't want to say it wrong because UV is a very, very good process in light-based processes, but uh, they change a styrene discharge to a burp. So there is no questions. UV is a very valuable tool in the toolbox. The thing that I think is important to understand that as you get into larger installations with UV, the complexity of the cure is needs to be assessed in the risk matrix because blowing the whole install and maybe to not take the plant out is as bad as taking the plant out. So yes, UV is on a there are things that will change the risk, but if you looked at the monitoring on this job, because UV, this was within the diameter range and within the toolbox of the contractors, UV was certainly permitted as an installation method with a different monitoring protocol in the context of what you would do and make it go away because you've still got to run sewage with it and UV can still basically reduce a residual styrene based on the quality of the degree of cure. It is obviously it's different in the context of cure water, but if you are not set up to monitor it, then you have an unknown, and we don't have a lot of data as to what those rushes are, other than that we do know that an incomplete cure will have a residual of styrene. It just comes out differently. It doesn't come out in a cure, and it is as I said, it's a tool in the toolbox. It's a very valuable one, but it's not a magic fix. It's not a button you flex, and it's not as simple as saying you take it away. So hopefully that answers the question.
Yeah, thanks, Chris. Just to add to that a little bit, when we're talking about UV cures, they and you did allude to it, Chris. You can't use UV in every application. You can't use
Yep.
CIP standard cure in every application, and that's something that has to be factored into it. Yes, UV cure does have typically a lower styrene discharge. I'm not sure what it's like in as you said, the water cure environment, but UV is a air steam, or sorry, air light type cure, as
Hmm.
opposed to water. So
Yeah.
those are things that have to be considered. But it's the same as considering UV and air water installs in any other application. Um, Another question was, how do you dispose of activated carbon loaded with styrene?
That's a really good question. It's actually really simple. It's like in the context of the way we've managed it when we use activated carbon jobs, we basically the beauty of styrene is that it's not that you catch it and it's there. Like styrene, the half-life of styrene, once you get it into a form, and that's what we found in the air inversion, like in the phase 3 studies, that handling of styrene to get rid of the VOC, the VOC that has not been, subject to phase change is about the simplest thing. I'll tell you, I'll give you a lesson just from earlier in my career, but I worked in Bristol Aerospace in rural Manitoba, who made rocket fuel, and we were chasing a different VOC, but we were chasing a VOC that was regulated at the part per billion level, and that VOC was, just heinous in terms of wow, the acceptance level was at something like 4 parts per billion, and it was found at 8 parts per billion. But we drilled in the groundwater for 3 years to find the plume, built a pumping station to basically draw the groundwater back to the plant so that it could all be treated. And I thought, wow, after spending 3 years of our life, chasing all this stuff down, the treatment process for this is going to be really complicated. The treatment process to get rid of it was to basically take it 50 feet in the air and drop it over a fan. Okay. Almost all of the VOCs come out of solution real easy. A VOC like styrene is about the easiest thing to get rid of safely in the world if you can capture it. So the activated carbon side of it, and I'll be callous, it's because it's kind of one of the things that, someone who spends their life doing treatment looks at optimizing treatment. So, and the way that we would deal with activated carbon on a site is we'll basically change the media out every job. So it's an expensive way to deal with it, but it's simple. But the disposal of it is very easy because the styrene comes out of solution very easy and is very easy to dispose of safely as long as you've got it in your hands. You've got it. Hopefully that answers your question. Silence, George. You're muted.
Stay, I think there, yes, I think there. Okay, we have a couple of more questions and 6 minutes to over the webinar. So the next question would be, Chris, to you.
Okay.
After how many days does the release of styrene fall below 0.1 milligram per liter?
How many days?
How many days does the release of styrene fall below 0.1 milligram per liter?
If it's asked how long did the discharge have to take? Like, I'm not sure what the question is, other than if it's asking how long it took for this job to get there, because it'll vary. But this job, I'm just trying to think. It was literally, it was. It will depend on how much dilution you're trying to achieve. So if I had another hour, I would show you the spreadsheet I use, but basically the relationship between, the the how much dilution you have to do will will do it. The bigger the flow of low styrene that you're mixing it with, or like no styrene type water, will lessen, will increase the rate at which you can discharge it for dilution. So uh, in this job, it wasn't a matter of weeks; it was a matter of a of basically discharging pretty well discharging this. I don't think, George, you could speak to it. You could probably answer the question, but I don't think the length of time through dilution, added a significant portion. It didn't add a week to the job or anything like that. It maybe added it added about as much time as it was as we were banking on to actually get the results from the lab, like an extra day or something like that to get the results in the lab to get it down to those levels. So it's not hard to achieve. It wasn't. That's kind of the lesson learned is that if you to the difference between doing this right and doing it in a matter of ignoring it was the matter of some planning in a couple of days, not it's not like an extra week. It didn't add a month to the job. It didn't add, it wasn't it wasn't that complex, and it is it doesn't take a long time, and it doesn't add a lot of time to the job in that context. Hopefully that's the intent of that question.
Thank you. And we'll have one last question from Tiffany. It says, "Hi, Chris. Thanks for the presentation today. Can you elaborate on what it means to use GAC more efficiently or effectively for styrene capture, and what are some methods for efficient use?"
If you would just repeat the
The
acronym again.
question. Can you elaborate on what it means to use GAC more efficiently or effectively?
Okay, yeah, okay, yep, yep. Granular activated carbon. In the context of the way that we use it, you, you it just it's like I said, the VOCs that we're taking out, and I can relate to this in other jobs, is that the the ability, and I pre this work in the Toronto region, the Greater Toronto area, we have done quite a bit of work with contractors where we're working in ravine areas. So we're in freshwater habitat, and in freshwater habitat, granular activated carbon is kind of the primary treatment mechanisms we'll use to basically treat the effluent to a level that makes it safe to put it into a receiving course for fish. Uh, from a practical perspective, one of the things I touched upon earlier was that uh, granulated activated carbon, like it's not cheap, so it is it's a cost to the job. But if you're going to use it, one of the things that we had determined that there's a subtle thing in the regulations is the regulations will allow you to discharge water, that smells like glue. I find as an engineer, I couldn't explain to someone that I was discharging something that smelled like glue. So when we use GAC, we push the limits, the acceptable limit for discharge to basically the non-detect level for odor. And that's kind of a practical consideration. But GACs are, again, if it was a more cost effective way and a more certain, at some point, if you're going to put granulated, like treatment on the end of it, you've got the same problem of where do you put all the water that you're doing? Do you know what I mean? Like, where are you putting this water? If you're right outside the treatment plant, where are you going to store all the water before you realize, t before you've measured it, got the temperature, understand the styrene is there. So the dilution like I said, is very valuable. It's very predictable. It's very reliable. It's about the simplest calculation you can do. Dilution in conjunction with activated carbon is again the less styrene you give activated carbon to take out, the more effective it is, and the easier it is to get to extraordinarily low levels, like to non-detect levels. So I don't know if that completely answered your question, but I'm doing my best to.
Thank you very much, Chris. I can see many messages in the chat with thank you notes to you for a great presentation. It was very meaningful, and thank you for sharing your expertise with us today. So
Thank
I
you.
also want to thank you to George for moderating the session and leading the discussion. And before we wrap up, we would like to also recognize and thank to all of our CUIIC members. If you could share the second slide, please, for me. Thank you.
Hard to train, I know.
Oh, good. Oh, good. So yeah, thank you to our CUIIC members. Your continued support and involvement help us bring the underground infrastructure community together and make opportunities like today's webinar possible. So thank you everyone for joining us today. We really appreciate your time and participation, and we hope to see you at our next CUIIC Academy webinar. Have a great day.
Thank you. Thanks very much. And thanks, George.